thank you very much for inviting me to speak at the summer school online. I'm an assistant professor at York University in Toronto, Canada. And my research area is actually machine learning theory. And what I would like to do in this, this mini course is give you a little bit of a taste of what type of questions learning theorists look at some basic techniques, and maybe later in the course also talk a little bit about current research. So more specifically, so this was my plan for the 4 sessions. So today we'll really just do an introduction to learning theory, talk about the basic notions, basic notation, do some warm-up exercises. So actually I'd invite everybody to get ready, maybe have a pen and a paper. Well, actually pretty much in the beginning start with some exercises. And then today also I just want to take you on a small kind of a historical tour of learning theory, talk a little bit about how learning theory has contributed to the development of some of the major machine learning tools. So I think learning theory is really an area where practice and theory kind of influence each other, which makes it a very interesting and exciting research area, I find. So that's the plan for today. Tomorrow, we'll get a little bit more technical. I'll take you through the some major techniques. I'll probably talk about VC theory and some other techniques to get generalization bounds. And then on Wednesday, I would like to talk a little bit more about more current research topics. Maybe I'll share a little bit of my research with you. And on Thursday, I understand the plan of the summer school is to have some sort of a fireside chat. So I'll look forward to that. So let's get into the actual topic. So I guess in this summer school, I don't need to motivate machine learning. So I don't need to talk about why machine learning is an exciting research area these days. So I'll talk instead about how we formalize it and how we mathematically analyze it, and what kind of guarantees we can give for machine learning algorithms. And at the very least for today's lecture, I will talk about supervised learning and about binary classification. So what you should have in mind is a binary classification task. So some sort of, you can, have simple example. Maybe you want to decide whether there is a cat in some image or not, or whether some email is spam or not, or whether some image is some brain scan shows a malignant tumor, or whether it's actually a benign, some benign growth, right? So we have a binary classification task. So typically we get training examples of the 2 classes, right? So here the blue and the red points will denote my 2 classes. And what I do is the task is given some data. What we'll do is we'll fit some function, we'll fit some classifier to this data. So here H, you will see, will always denote my predictor. Can you actually see my mouse? Do you see my cursor?
Yes, we see it.
Yeah, okay, good. So H is the predictor. We fit some function, some predictor to the data. And then what is the actual goal? The actual goal is not just to fit some function to the data, but instead, when some new data comes, once we've learned a predictor, comes a new data point, what we really are after is make a correct prediction on this new data point, right? So here comes a new data point whose label we don't know. We don't know whether this email is spam or not, or we don't know whether this tumor is malignant or not. We want this predictor to be so that it gives us a correct annotation for a new unseen data point. So really the question we're after is how well will H predict on new unseen data points? This is somehow what the whole story of supervised learning is about. So now I'll take you through the formalism. So a little bit of a warning, the next slide will have lots of notation, and I'll probably encourage you, once the slide is fully built up, to maybe take a screenshot just so that you have the notation ready for the rest of the talk. So here's how we formalize this supervised learning setup. So our data points, right, so we can have this binary classification picture in mind. The data points they live in some feature space. So X will always be some feature space. The feature space, and typically this is some sort of a lower, depending on the task, lower high dimensional Euclidean space. Maybe we took some measurements. Maybe this feature space represents some images, right? So the feature space, the instances live in some sort of Euclidean space, we'll assume for this lecture. And the label set in a binary classification task is just two different labels, say positive or negative outcome, 0 or 1, +1, -1. And then the input to a learning algorithm is a data set, right? So we have a data set that is just a sequence of feature vectors with labels. So we assume that the learner gets annotated data as input, and the predictor is just any function from the feature space to the label space. So it's just a function from this Euclidean space to, in this case, 0 or 1. Right, and the question is, how do we actually measure how well a predictor does? So typically we measure this, or in order to measure this, we need to specify a loss function, right? And in binary classification, the most natural loss function is just a binary loss function. So here, so L will always denote my loss function. Loss function is always a function that takes in a predictor and an input and an output. Right, so it takes in a predictor, an input and output, and we want to decide the loss function should somehow measure how well is this predictor doing on this input-output pair. So in binary classification, really what we're asking is just, is this predictor giving me the correct classification on this example or not? Right, is h of x actually, does it correspond to the label that was observed in this, the true label of this example? So this is what we call the binary loss function. If you have a regression task, then you probably want to use a different, then you want to have a loss function that somehow measures how far is the predicted output from the true output, from the true target. So loss function is a function that measures how well we're doing. And then once we've specified the loss function, we have a data set, what we can always compute is an empirical risk, right? So the empirical risk is just we're averaging this loss function over our data set, right? So I'm just, if I have some data set, my predictor, maybe I have 100 data points, my predictor makes 3 mistakes, so I'm counting 3 over 100, normalized by the size of the data set. This is going to be my empirical risk. But now, as we already said in the previous slide, we're not really just after having a low empirical risk. We want to actually do well on new unseen data points. And since we don't know what the actual process is that is generating the data, if we knew exactly what the process was that is generating the data, we didn't need to do any learning. There would be no need for machine learning. So the unknown quantity in this whole setup is the data generating process. And how do we mathematically, we model this uncertainty, the unknown, we model it as a distribution. So we say the data generation is a distribution over the product space, the input times the output. So this distribution actually generates these type of examples. Right? So this is kind of a modeling of what is uncertain in this whole setup. So we say the data generation, we model it by a probability distribution. And then the basic assumption that is behind most of the approaches is that our data is an IID sample from this distribution. And the learning algorithm then is an algorithm, and here for now we'll just think of this algorithm again as a function. It's just a function that takes in a data set and outputs a predictor. Right? So learning algorithm takes in as a function. Really afterwards we'll actually also want to think about, is this an algorithm, is this an efficient algorithm? But for now we'll just think of it as a function that takes in a data point, outputs a predictor, and then the goal, now we can formally phrase our goal. The goal of a supervised learning setup is to say we want to find a predictor H, that is the output of our learning algorithm on the data set. So A of S, learning algorithm, gets the data set as input, outputs a predictor, and we want this predictor to have a small true error, or the true loss. And what is the true loss? Well, the true loss is the expected loss over our data generating distribution. Right? So whenever we have a loss function and we model our data generating process as a distribution, we can say, well, our goal really is to get a small expected loss. right? And if you have a binary classification task, you can also think of this expectation. This loss function is binary, just take 0, 1 values. This is actually the same as, you know, say you draw a new data sample from your distribution. What's the probability that this predictor, that this classifier misclassifies the input, this input output pair, right? So this is what we want, that the probability that a new point is misclassified is actually small. So this is the slide that I would recommend. Maybe take a screenshot just so that you know what notation I'm using, right? So I'll just like wait half a second. So everybody feel free to take a screenshot or take a picture so that you have this notational setup ready. Okay, so now the challenge is actually that we don't know what the true data generating distribution is. We only get to see the data set. We can compute an empirical loss, and really what we're interested in is, you know, how close is the empirical loss that we compute? How close is that to the actual true loss? Right. So now I'll get to the first quiz already. So everybody has this notation hopefully recorded in some form. So here's the first quiz. So I'll claim that given any predictor, so I can take any classifier. So it's from my feature space to 0, 1, we're in binary classification setup. N is my sample size, so I have so and so many data points. Then I'm claiming for every data generating distribution P, so no matter what the data generating process, the expectation over the empirical loss is the true loss. So in my quiz is now, let me show you the quiz. So what I'm asking you, is this true for any fixed sample size N? Is it not in general true for fixed sample size N? C, is it maybe only true for large enough N and that N should depend on P? Should it be true for large enough N depending on H on my predictor, or is it only true in the limit? I could also maybe this expectation will converge to the true loss, but it's not, it's never actually equal. So I don't know. Can you do the quiz? Can we do a poll? What do people think?
It's now live, so participants can just have to click. They just have to click the link on the Zoom chat, and they will be taken to the poll with the options.
So do I have the chat here? Actually, I don't see the chat.
The link is already in chat, and they will be
so now I go to this link.
So we are getting answers on the poll.
Okay.
So this is changing. So there's a clear winner so far. So we'll wait a bit to share the answer.
Okay. So I'm not actually inside the.
So
so just wait a moment, let everybody think. Maybe yes. Once you see some trend, let's see what.
Well, already on the chat box, we have a very clear trend.
Okay.
Also on the poll, the option number E is by far the number one with 80%. Number A is 20%, and all the others 0%.
Okay. Which one is 20%?
A.
A. Okay, so we have kind of bimodal. Some people think A, many people think E, nobody thinks B, C, or D. Yes. So that's interesting. So let me show the answer actually to this quiz. So my claim was that for any distribution, the expectation of the empirical loss is the true loss. And the answer is this is actually true for every fixed sample size N. And so it's interesting to see the result of the poll is somehow what I would have expected. So the tendency, of course, is to say, well, we first need to see enough data, and then maybe once the data set is large enough, we get a good estimate of the true loss. But here, actually, if we just look at a function, we look at a fixed function, and we look at, you know, what is the expectation, even if I just draw one one sample point, this is actually exactly the true loss. So even if I have just sample size 1, very small sample size, the expectation of the empirical loss is actually the true loss. And we can also just quickly go through this mathematically. So if we wanted to calculate, if we want to clarify to ourselves why this is formally correct. So here I'm just writing out now the expectation of the empirical loss, right? So this expectation, this is how I define the empirical loss. So the empirical loss is I average over my data set size, how many mistakes did I make? Now the one thing you need to remember here, if we want to do this little calculation, is that an expectation is always a linear operation, right? So expectation is a linear operator. So what that means is that I can take this constant here, the 1 over n, I can take it out of the expectation, and also the sum, I can take it out of the expectation, right? So since an expectation is a linear operation, I can take this out, and I'll get actually an average over this expectation. And now, so here from 1 to n times, I'm now sampling a size of n, a sample set of size n, but I'm only looking at the ith data point in this sample. So really, I don't need to sample a full set of size n here, right? I can just sample 1 point. So this is the same as just sampling, averaging 1 over n, sampling 1 point. Am I making a mistake on this 1 point? And this is actually exactly how we define the true loss, right? So now I'm n times, I'm summing up the true loss, and then I'm dividing by n, so I'm actually getting exactly the true loss, right? So this is a very good thing to remember, right? So the expectation, we see the correct thing. We are after a function that has a small true loss. On expectation, we see the correct thing even on small data samples. So now let me make a new claim. So this is the second quiz. So now I'm claiming, so let n be some sample size. We just got optimistic. We said, okay, for any sample size, if I draw data from my distribution on expectation, I see the true loss. So now, again, let n be any sample size. Then for all learning algorithms, I'm claiming, and for all distribution, the expectation of the empirical loss of the output of my learning algorithm is the true loss. So what about this one? So I'm giving you the 5 options. Is this also true for any fixed sample size n? Is this not true for any n actually? Is this true for large enough n depending on the distribution p? Is it true for large enough n depending on a? Or only in the limit as n goes to infinity? So I guess we can do a quick, I'll let you think about this one a little bit, and we can do the quick poll.
Yes, the poll is very live on Slido, so people can already start voting.
Okay. So I'll just wait for,
yes,
once we see some trend, let everybody think a little bit. So do we see any?
We are starting to get the answer, so people are still voting.
Okay.
Changing. So we have, with 40% of the respondents, answer E as the number 1.
Mm-hmm.
In place number 2 is answer A with 30%.
Mm-hmm.
And we have B, 13%, and then C and D with 6%. So it is in E and A. Now A has been growing as well. So
right. So it's people got more confident in A, but it looks very similar, but it's a little bit more mixed. Right. So this statement actually, it looks very similar to the statement before. And one could, of course, then be tempted to go for the same answer A. But I guess as students, you could guess that if the answer was the same, maybe I wouldn't have asked the same question. So let's resolve this quiz. So here my claim is for any learning algorithm for any distribution on expectation over the empirical laws, I will see the true loss. Right. So this is actually as stated like this. It's not true for any sample size n. So this statement as a whole is not true for any sample size n. So if we now look back at the question, so I'll resolve this quiz in a moment. Of course, here one could have actually answers n depends on the learning algorithm or on the distribution. This could also have been, you know, correct to some degree, but if I take the statement as a whole here, for any algorithm, for any distribution, the expectation of the expectation of the empirical loss of the algorithm's output is a true loss, then this is actually not true for any sample size n. So let me just give you a small proof and convince you why this is not correct. So what I'll show you is that there exists, so if I want to negate this statement for any learning algorithm for any distribution, I will need to show you there exists a learning algorithm and there exists a distribution such that this thing is not true. So I'll show you an even stronger statement. I'll show you that there exists a learning algorithm and a distribution such that for any sample from this distribution, the true loss will always be 1 and the empirical loss will always be 0. So I'll design a learning algorithm that on this particular distribution does really poorly in the sense that it has a very small empirical loss, but a very large true loss. Right, so that's very different from what we saw before. So let me just take you through this small construction here. So I'll design a distribution in learning algorithm as follows. So I just look at, say, a 2-dimensional feature space. So my feature space, say, minus features taking values in -1, 1. I have 2 features. I look at a distribution that is uniform over this feature space and always produces examples with labels 1, right? So I could think of, I don't know, maybe I have to do like a small surgery, and you know, I look at some hospital's record on this small surgery, and you know, depending on, I don't know, the say the time of the day and the experience of the surgeon, actually this surgery is such a simple surgery, it always goes well. Right, there's always positive outcome. But my learning algorithm, so what this actually means, so if the distribution always produces positive examples, then any sample from this distribution will look as follows, right? So I see some feature vectors and always with a positive label 1. So it's actually a really nice world that we're living in here. But my learning algorithm is very pessimistic. My learning algorithm does the following. The learning algorithm, so remember A of S is a predictor, right? The learning algorithm takes an sample S and outputs some predictor. So we can apply this predictor to a new feature vector X. So now this learning algorithm says, well, okay, if I saw the sample, this particular point, I saw it already in the sample, I'll agree, I've seen it with a positive label, I've seen the surgery on this particular patient went well, okay, I agree, this is a positive, but any other case, I'll keep pessimistic. I don't believe, I'm very scared of my surgery, so I'll just keep believing that all other cases is going to have a negative outcome, right? So this learning algorithm, it does perfectly well on the sample, right? It does perfectly well on the sample. As soon as it saw some data point in the sample, it will admit that this was a positive example, but everywhere else, it'll keep believing the label is 0, it's a negative case. Right, so now we have that the empirical loss of this, the outcome of this learner will always be 0, just by design. But the true loss I'm claiming is actually 1. Why is this? So I don't know if we can allow people to put something in the chat or say a few words. So can anybody tell me why in this case, the true loss of this predictor that the algorithm output on this distribution, why is the loss 1? So the predictor says 1 on the points that it saw in the sample. Everywhere else it says 0. Anybody has an idea? I don't know if I can open the chat. right? So somebody says measure of set is 0. Why? So let's go back to this example. I mean, this is a correct answer, right? So the point here is that I have a uniform distribution over this uncountable space, and any finite, a sample is always finite. So this predictor is correct only on a finite number of points, but on all the rest of the domain, the predictor is still incorrect, right? So a finite number of points in a uncountable space, distribution over an uncountable space has measure 0. Therefore, the true loss of the output of this algorithm will be 1. So this algorithm actually does really poorly. It gets 0 mistakes on the sample, but full loss 1 on the actual distribution. So what did we see so far? So we saw, in quiz 1, I'm claiming for any age, for any sample size, and for any distribution, the expectation of the empirical loss is actually the true loss. And now in quiz 1, I said, well, there exists a learner and there exists a distribution such that no matter what the sample size, the empirical loss and the true loss will be really far from each other. So the empirical loss of the predictor that I see on this data set for this learning algorithm is not a good indicator of what its true loss is at all. So now my question would be, is there a contradiction? So what is the difference between these two setups? So why can they both be true, or did I cheat you somewhere? Anybody has any? So I see somebody said something on the chat. Right, so this was still to my previous question. No matter how many sample points you sample, there's always an infinite number, an uncountably infinite number of points that I don't sample. That is correct. So what is now going on in this situation here? So why aren't these two statements contradicting each other? And if not, why not? Where's the difference? What's the crucial difference here between these two setups? Why is in this case the empirical loss seems to be a good indicator of the true loss, but in this case, it's not a good indicator of the true loss at all? Right, so here somebody says, A of S is the hypothesis we learned from the training set. Exactly, yeah. And this actually, in fact, it points in the right direction. So the crucial difference here is that here I fix my function that I'm testing, I fix it, and then I sample. And for any fixed function, the expectation, if I just test this one function, I actually on expectation, I see the correct thing. Here, so here as one of the participants says, here my function actually depends on the data. So here my function was fixed before I sample a data set. Here my function in contrast actually depends on the data, and that is a crucial difference between these two situations. So here this is the answer. So in the second claim, the predictor H, which is the outcome of my algorithm being fed a data set, it depends on the data, whereas here it was fixed and we just test this one function. So this is a crucial difference. But now, of course, in machine learning, we're actually in situation 2, right? So this is very important to keep in mind. In machine learning, we don't want to just test one hypothesis. We want to do more than just fixing a predictor and test this one predictor's performance on some data generating distribution. But what we actually want to do is we want to fit a function to the data and hope that this function that we were fitting with some algorithm to this data set will perform well on new unseen data, right? And here in this situation, things actually can go wrong pretty badly. So here, just to conclude, first, small lesson learned. So in machine learning, we want to output a predictor that is learned from data. But in general, if we're in this setup, if the function, the predictor H, depends on the data, we cannot just assume that the empirical loss is a good indicator of the true loss. So we just saw an example where this goes really badly wrong, right? And so you probably know this. What we need to do is we need to have some way of preventing overfitting. So this phenomenon that I showed you here with like a very constructed artificial example, this was kind of a drastic case of overfitting, right? So if we look at this example again, so here really my learning algorithm, it was just adapting itself to this particular data set really, really well, but being stubborn completely on the rest, right? So it just believed that the world is negative, and it keeps seeing positive examples, but doesn't change its basic belief. It admits on every data point, I've seen this case now, I admit it's a positive case, so I'm adapting myself to the data set, but I'm not adapting my general belief at all, right? So this is what I call the stubborn learner. So the stubborn learner overfits really, really badly. So the phenomenon here is that this learner has way too much flexibility to adapt its output to any particular given data set, right? And what we'll take from here and what we'll see in this course is that one way to prevent such a phenomenon from happening, one way to prevent overfitting is that we somehow want to restrict the learner to a fixed beforehand fixed set of possible predictors. So we saw if we just fix our set of possible predictors to just one function, then we can test this function as an expectation. We're going to see the true loss, right? So we don't want to just test one function, but we also don't want to allow the learner to adapt itself completely on any data set it may see, because then things can go really badly. So we want to actually find some sort of middle ground between testing just one function and allowing the learner full flexibility to adapt its output in any silly way. I mean, this definitely is kind of a silly way of the learner to adapt its output to the data set that it saw. Right, so this is what we're now going to look at. This is kind of the program of classic statistical learning theory. So what we actually want to do is we want to fix a hypothesis class. So I call a class of functions, class of predictors from my feature space 201. Call it the hypothesis class. And what I'm going to define my success criterion relative to this fixed hypothesis class. So I'm going to say, well, I know that I somehow have to restrict myself. I cannot allow my learner to just output anything, but then of course I can only expect to do as well with my overall learning performance as this hypothesis class fits to the actual task that I'm trying to solve, right? And the measure that captures this phenomenon, it's called the approximation error of the class. So this is the infimum over all hypotheses in this class of the loss with respect to the distribution that I'm looking at, right? So we are asking ourselves, if we chose, say, H, this can now could be a class of linear predictor, or it could be a class of decision trees, or H could be the class of neural networks with a certain architecture, or it could be maybe some random forest. But I'm fixing the type of predictor, right? And then I'm adapting my success criterion. What I'll do is I'll say, well, I hope that that the output of my learning mechanism will be at least as or close to the best possible I could do with this fixed class of predictors. Right. So here's now definition, standard statistical learning theory definition of learnability. Right. So what we want is that we say that an algorithm A, which right now still is just some function, algorithm A learns my class H if for any epsilon is my error parameter, delta is going to be a confidence parameter. For any epsilon delta, I want there to be a sample size such that for any distribution P, so here now we're making a high probability statement, right? We want that something good happens with a high probability 1 minus delta. What is this something good? I want that the true loss of the output of my learner is close to the best possible I can do with my fixed hypothesis class. So this is going to be my goal. This is once I realized I have to somehow restrict my class, this is as good as I can hope for. And what I want is that with a fixed given data set size that depends just on my epsilon and confidence parameters, I'm guaranteed that for any distribution, I'll be close to the best possible. Right? So this is called a distribution-free finite sample bound. Distribution-free because I have this requirement that it should hold for any data generating process. And if such a learner exists, we call the class H learnable or PAC learnable. Are there any questions up to this point? I can quickly check the chat. Anybody has a question?
So far, there are no questions on the chat.
No questions? Okay, so I'll just continue. Okay.
There is a question asking what is a PAC, probably approximately correct. So you will get that?
Right, so for a PAC is probably approximately correct. I'll get to this, in a moment when I do my small historical tour, why it's called PAC. I hope I'll actually get to my historical tour. Right, so PAC, probably approximately correct. Probably here that stands for the delta with high confidence over my data draw. I want to be correct. Approximately is my epsilon. I want to be close to the best in the class. And correct is I'm looking at the loss of my output predictor. Any other questions? Okay. So now then the question, so the very basic initial question of statistical learning theory is which classes are PAC learnable? And what we'll see probably tomorrow is that for binary classification, classes is learnable if and only if it has finite VC dimension. So there's a parameter of this class, a characterization of this class that will tell us whether this class can, whether there exists a learning algorithm for this class that will satisfy this definition of learnability. In particular, what we'll see, and I want to quickly show you this today, and we'll have 11 minutes. So I have to speed up a little bit for this last proof, but you can look at the slides afterwards. So in particular, every finite hypothesis class is learnable. And learnable here will actually be possible with empirical risk minimization. Empirical risk minimization for these classes, for classes of bounded VC dimension or finite hypothesis classes, empirical risk minimization is a successful PAC learner. So what is empirical risk minimization? Empirical risk minimization is essentially what we intuitively want to do. We get a data set, we have some type of predictor that we're considering to use. So we just want to find a predictor that makes small number of mistakes on this data set, right? So empirical risk minimization for, let's see if I can move this. So given a hypothesis class, right? So we fix our type of predictors. The learner A is an empirical risk minimizer. We'll call it ERM. If given a data set, it'll output a function that has smallest possible number of mistakes on, or smallest possible loss on this data set. Right? So the algorithm outputs a predictor, and when we'll talk about empirical risk minimizers, we denote these functions by h hat. It's kind of standard notation that I'll also use. So h hat is an empirical risk minimizer function from the class that makes in binary classification fewest numbers of mistakes on the given input training data set. And so that's a general learning paradigm. So now we'll see one small theorem today. So I'll show you that finite classes are actually PAC learnable. So for finite, if I only have finitely many functions in my class, so let's assume my class is h1 to h capital N. P is any data generating distribution. I'm setting myself a goal, some delta confidence parameter, and I'm claiming the following: with probability at least 1 minus delta of the draw of an IID sample, we have, so now let's look at this statement, that the true loss, so this is what I'm after always, right? So I have my empirical risk minimizer h hat. The true loss of my empirical risk minimizer is bounded by the true loss of h star, and h star, I'll now just give a name to the best possible predictor in my class. So I told you before, once we fix a class, we can only hope to do as well as this class fits my problem, right? So H star is, we use this notation for denote the best possible predictor in my class. So my empirical risk minimizer, the loss of my empirical risk minimizer is bounded by the loss of the best possible in this class, plus a term here that depends on the data sample size. So n is the size of my data sample. So I see here I have an error term that goes down as we see more and more data points. Right? So this is the type of statement that we want. So in order to prove this, so I'll probably chase you a little bit through this proof now. So we use, and this is kind of standard technique, we use in concentration inequality. So here we'll just use Höfting's inequality. So we have some ID. So they need to be independent. They actually don't need to be identical, but here we have identical independent random variables that taking value in 0, 1. Then Höfting's inequality, it gives us a bound of if we average our observations, right? So the empirical averages of my random variable, how far are they from the expectation of this random variable? So it gives us a bound that if we see n observations of this random variable, then the probability that the empirical averages is epsilon away from the expectation is bounded by this term here that goes down with the number of observation I made. This is kind of a standard tool. So how are we going to use this? So we want to show that the true loss of my empirical risk minimizer is bounded by the true loss of the best in the class plus this term, right? So let's see, how can we get a bound here? So first thing I do is I just bring this true loss of H star, I bring it to the other side. So I'll just want to bound this difference, right? The true loss of my empirical risk minimizer minus the true loss of H star. So how can I bound this? The first thing I do is I subtract the empirical loss of the empirical risk minimizer plus and add the empirical loss of H star. So, and here I'm claiming now I only made the expression larger. Can anybody in the chat tell me why is this step correct? I don't know if somebody is still, let's see if anybody's still awake.
We are.
You are awake. Any idea on why this is correct? Or I'll just wait like very shortly. Triangles inequality is actually even simpler. It's very simple. So I was subtracting something and I was adding someone, introducing 0. It's not 0. So I'm claiming here it could be potentially larger than 0. Why? But why is it always larger than 0? So I'm what I added here is always larger than 0, I'm claiming. So by definition of H star, exactly, yeah, that's half the answer. So by definition, H star is the best from the class, exactly, H star is the best from the class, but with respect to the true loss. So H star is best in the class with respect to true loss. So what I also need here actually, so maybe I'll just move on now, but this is half the answer. So it's by the definition of H star and H hat. H star is the best, is a function in the class that has the best true loss, but H hat is the function that has smallest empirical loss. So I'm subtracting something, but then I'm adding something larger. So H star always has at least as much empirical loss as H hat, because by definition, H hat is the empirical risk minimizer. Right, so here I only made this expression larger. Now, and now it gets very simple. So now what I'll do is I'll add some absolute values. So let's see here. So I just took the same expression, added absolute values here. So again, I made things only larger. And now I'm saying, well, now I have twice this, I mean, I have this expression here, empirical difference between empirical and true loss. I mean, this is the quantity you'll realize that I'm kind of obsessed with in this lecture, right? What is the difference between the empirical and the true loss, right? So here of H star, here again, difference between empirical and true loss. Oh, here's the P is missing. Difference between empirical and true loss of H star. So I can bound this by 2 times the largest possible difference in my class H between empirical and true loss, right? So now what this shows me is that if I can bound this quantity, if I can somehow for all functions at the same time bound the difference between the empirical and the true loss, then I get a bound on this quantity, and then I get the error bound that I was claiming at the beginning. Right, so this is actually, so maybe let me just mention this term. This is what's called uniform convergence. If we can uniformly, for all functions in the class H, we bound the difference between the true loss and the empirical loss. And then we have what we call uniform convergence. And that will get us the result that we're after. So now to prove this uniform convergence here, we'll use Höfting's inequality. So we'll fix a function h first now. We fix a function h, and we'll set our random variable is, what is the mistake that h makes on a data point, right? So I have n instances of this random variable. So that did I make a mistake? Did h make a mistake or not? So if we now plug this in, so this was the expression we saw in Höfting's inequality. So now in the language of the classifier that makes mistakes, this translates directly to the difference between the empirical loss and the true loss. So what is the probability that this is larger than epsilon? Well, now we can bound this. With this expression from Höfting's inequality. It goes exponentially down with the number of data points that I saw in my sample. So this is more like the situation in quiz 1, right? So in quiz 1, we were just talking about one function, right? So for one fixed function, we can bound the difference between the true and the empirical loss simply with Höfting's inequality. We actually want to do this for all functions in our class, but since our class was finite, this is now also simple. So this was the quantity we wanted to bound, right? The true loss of the empirical risk minimizer minus the true loss of the best function in the class. We saw that it's bounded by 2 times the sub over the class. So here we can say, well, this is larger than epsilon only if the maximum difference that we observe in the class is at least epsilon over 2. So this is equivalent to saying, well, when is the maximum over my class larger than epsilon 2? Well, when there exists at least one function in my class for which it's larger than epsilon 2. So either for the first function in my class, true loss minus empirical loss is larger than epsilon over 2, or for the second function in my class, true minus empirical loss is larger than epsilon over 2, or for the third, and so on. So I have this big OR expression here. So now I can remember my basic probability theory, and I know that in OR of events, I can use the union bound and turn this into a sum of these, the probability of these each of these events, right? So for every function, this is actually the same probability, and we bounded this with Höfting's inequality. So I get the size of my class times this expression from Höfting's inequality. And now it's really just a little bit of calculation. I set this to be my confidence parameter delta. I solve for epsilon, and then I'll actually get exactly the type of statement that I wanted. Right, so the probability that the true loss of my empirical risk minimizer minus the true loss of the best function in the class is larger than this expression, this is my epsilon now, is bounded by delta. So now I showed you, and I realize I'm out of time. So this is the theorem that I showed you. So I showed you now that finite classes are packed learnable. So maybe I'll take a break for questions. Maybe I move the historic tour to tomorrow, or what is the? Yeah. So so welcome to my my second lecture. in the summer school. And so just to remind you briefly of the plan that I had for this learning theory mini course. Yesterday, my plan was to end with a small historical tour actually of machine learning theory. We didn't get to it, we ran out of time. So I'll start with that today. I'll start with, actually telling you a little bit of stories. So in the beginning, it won't be too technical, but it'll also serve as a reminder, as a small recap of the concepts that we were talking about yesterday. And then today, I'll stay in the very basic regime. I'll talk about some basic concepts and technique in statistical learning theory. In particular, I'll tell you about VC theory and no free lunch results. So I'll tell you about, or give you an idea about how to prove lower bounds in statistical learning as well. But yeah, as I mentioned, I want to start with taking you a little bit on a history tour here. So, so let's see how this whole story developed. So the basic question, and this relates to what we talked about yesterday, that we're interested in statistical learning theory, in particular in theory of, yesterday I talked, and actually that will stay the same for the day. Today I'll talk about binary classification. And the basic question that we're interested in is how well does the error of some predictor, of some binary classifier that we observe on a data set, how well does that actually represent the error, the true error of this predictor? How well does it represent the data, the error of this classifier on the underlying data generating process? So here's a very, very simple equation. So as I said, we'll start very slowly here. So the true error is always upper bounded by this trivial inequality here, right? So the true error, we can write it as the empirical error. So this is the loss that we can observe on the data. So in binary classification, we would just count how many mistakes does this predictor make on the data set. So this quantity here we observe, and then plus the difference between the true error and the empirical error. So this quantity that we were yesterday already starting to get obsessed with. We are interested in bounding, ideally for many classifiers at the time, the difference between the true and the empirical losses. So the empirical losses is something we observe, the true loss is something we cannot observe. So we want to have some sort of control over this. Right, and ideally what we want is that this, what I call here the generalization error. So the generalization error is this difference between the true and the empirical losses, that it is somehow small. So I call it here an epsilon, and it's kind of a function that goes down with the amount of data that we see. Right, so we want this generalization error to be a function of the data set size. We want it to go down with the amount of data that we see. So let's see how learning theoreticians have looked at this issue over the decades, we'll say, right? So we'll start with the 70s. So in the 70s, there was Vladimir Vapnik and I think Alexei Chervonenkis, so two Russian statisticians that came up with this basic theory that we're essentially still teaching today, that really can control this generalization error in a setup that is more than just hypothesis testing. So yesterday we saw that there's this difference between testing just one hypothesis, right? So if we just have a fixed function in mind and we just want to test what is this function's error, then we can just draw our data. But we also saw that if the function can depend on data, then the empirical and true losses can be arbitrarily far for the theory that was developed. We can control this generalization error binary classifiers has Mencke's. So we get this bound here, the empirical minus the true. And this is true for all functions in the class simultaneously. So we have uniform convergence. As we see more and more data points, we have uniform convergence over all functions in the class. The important point is this was really a statistical result. This is not really talking about learning algorithms yet. This is purely statistical convergence of certain estimators to their true expectations. All right, and then in the 80s, actually, I mean, this also started in the 70s, of course. In the 70s, there was the Cook-Levin theorem. People started, or researchers started, or developed the theory of NP hardness, started getting interested in computational complexity and how we can formalize actually computation and runtime in a systematic way. So this also entered this the analysis of learning. So in the 80s, Valiant came up with wrote a seminal paper, theory of the learnable, and introduced the concept that we also saw yesterday of packed learning. So I'll just briefly go as a reminder, go over this definition again. So we say that a class age of binary predictors is packed learnable, and I think somebody already mentioned this yesterday. Packed stands for probably, approximately, correct, learnable. If there exists an algorithm, and now really the emphasis is put on an algorithm. So yesterday, actually, we just thought of the learner as some function that maps a data set to a predictor. But here, now we have an additional requirement. So if there exists an algorithm such that for all epsilon error parameters, epsilon confidence parameters delta greater than 0, there exists a fixed sample size that will give us a guarantee for all possible data generating distribution. And now is the important addition here, the algorithm computes a predictor in a polynomial time, polynomial in 1 over epsilon, 1 over delta, and typically we also want it to be polynomial in some sort of parameter of the hypothesis class. And then this algorithm that runs in polynomial time gives us this type of guarantee that we saw yesterday, that the true loss of the output predictor is close to the best possible we can achieve with our chosen hypothesis class. Right? So this was a new aspect that was added to this so far purely statistical point of view. And then in the 80s, for binary classification at least, we kind of already understood the statistical aspect. So there was this previous characterization of Rudnick-Scherbonenko that we know we can control the statistical aspects of this problem if the class has bounded VC dimension. What was also already developed in the 80s is a notion of compression. So if we can compress a data set, the labels of the data set to a small size, small compression size, and recover the labels that came from our hypothesis class, then again we get generalization bounds in terms of these compression sizes. So this was already understood. So this concept of if we want closeness of empirical and true losses, somehow the class needs to have bounded capacity, and that's what we saw yesterday as well. But that what also became clear is that if we wanted to add this computational aspect, the computational requirement, then turned out that for many classes, and at that point people were mostly looking at Boolean function classes, but it already became apparent that for many classes, if we actually want to do empirical risk minimization, if we want to find for a given data set predictor that output that has a minimal number of mistakes on this data set, then this is computationally actually a hard problem. So so then what happened in the 90s is that these aspects of statistical and computational considerations started to play well together. So so there were more and more hardness results, but there were also now we also saw an emergence of actual practical learning tools. And here are two that actually came out of this interplay between computational and statistical complexity. So so this is actually so the story here on the left side of boosting. This is actually, I think it's a very nice example of how seemingly pure theoretical results can actually lead to the development of practical learning tools. So so the story here is that it was known that strong learning meaning what I've showed you before, that if we want to achieve arbitrarily small error parameter epsilon, so for certain classes, guaranteeing arbitrarily small error epsilon was known to be a hard problem. But then Rob Shapiro, so there was this question, maybe if we ask for less, maybe if we ask only for our constant fixed error. So if we only ask for, you know, we don't want to achieve arbitrarily small error, but we want to achieve, say, error epsilon, error third, right? So if we weaken the requirement of the learning algorithm to only achieve error, say, third, can we then get an efficient learning algorithm? So what was first shown here is that was a reduction. So it was kind of a hardness reduction that said, well, if we that weak learning is as computationally as hard as strong learning, as achieving arbitrarily small error. But then this reduction, this hardness reduction, was actually turned on its head and turned into what we know as boosting. That is to say, well, let's just assume we have a weak learner. Maybe we don't, but let's just assume we have a weak learner. So we can turn this reduction into a tool that will actually allow us to do strong learning. And this is what we know as boosting. So we have a sequence of learning steps where we just shoot for, you know, a constant size error on a re-weighted data set, and then combine these weak learners in a majority vote to actually have small error over the actual prediction. So this was one example where theoretical considerations turned into what was then actually, and it still is actually a pretty successful learning tool. The other story that also started in the 90s, so it's the same researcher Vladimir Batnik that was played a crucial role here in the development of support vector machines. So his story is somewhat similar, that we knew that for linear half spaces, we can train them efficiently if the data is separable with a large margin. I think you actually you saw statement like that in Zach talks now just at the end. So if data is separable with a large margin, then we can computationally efficiently find an empirical risk minimizer. But often data is not linearly separable with a large margin. So here was what was developed is the theory of kernels, so of similarity. So we can use somehow distort the space by using a kernel function, and this allows us to map our original data space into a higher dimension, potentially infinitely dimensional feature space where now the data becomes linearly separable with a margin, and that allows for efficient large margin separation. So this is development of kernelized support vector machines, and the initial researchers that are important to have in mind here is Vladimir Vacnik and Corinna Cortez and Bernhard Schulkopf, Alex Moller. So then in the next decade, so there were now we had a bunch of successful learning tools, and the next decade, from theoretical point of view, we can really say we got a better and better fine-grained understanding on which type of tools can would lead to generalization. So for example, Rademacher complexities give a little bit of a more fine-tuned handle on generalization properties for various loss functions. VC dimension is really just talking about binary classification. Rademacher complexities we can use to analyze arbitrary loss functions. Data-dependent generalization bounds, and more of these tools took into account properties of the data, large margins, that allowed us to get a handle on generalization properties of, say, regularized risk minimization approaches, pack-based bounds, compression bounds, algorithmic stability. So we develop more and more tools to understand when the outcome of a learning procedure would actually have a good generalization error. And then another 10 years later, around 2010, I think 2011, is really when the success of deep learning took over. And from a purely theoretical point of view, this was somewhat disturbing. So very large networks, we saw solving very complex learning tasks, mostly on image data initially. And from a theoretician's point of view, there are a few issues. So these classes that were used to train these image predictors, they have huge capacity. So from our understanding at that point in time, really they shouldn't have generalized, right? And also we shouldn't be able to train them. So loss minimization is computationally hard for neural networks, and these optimization problems that we encounter in large neural networks, they're very much non-convex, and it's unclear why the algorithms that we use, why would they actually find a minimum first, and why would this minimum that it finds, why would it output a predictor that has good generalization properties? So there was really quite a few mysteries, but there was still some of this belief that there must be some inherent property, either of the learning method or of the type of predictors that we use, that will lead to generalization. And then now a few years ago came this paper. And we've heard about this. So in 2008, I think it appeared on Archive in 2016 and ICLR in 2017 by Zhang, Ben, Geohard, Rechte, and Vinyals. So they conducted a bunch of experiments that were somehow even more disturbing to theoreticians. So they did the following. So they trained some, I think on image data, they trained deep neural network with the labels that were provided in this data set. So what they observe is, well, we can drive the training error down to 0. That will also get us a small test error. So the error on a test set is also small. So this means exactly, so the difference between the training loss and the true, I mean, here represented by some test loss, is small. So we would say, well, this generalizes well, right? So this quantity here between true and empirical training loss is small. And then what they did is they said, well, what happens if we permute the labels on these images? So now we're training on the same input data, but with permuted labels. So from the label perspective, essentially we train on random noise. So what happens is that the training error still went to 0, but of course there's a large test error because there was no signal in these in the labels. So this doesn't generalize. So here we have a large difference between the training and the test loss. And the somewhat surprising thing here is that the way this experiment was set up, both the class of predictors and the algorithm, the training method, were identical. So it seems like whatever leads to generalization in deep learning, it can't be just the hypothesis class and it can't be just the algorithm. It must be something else. There's been quite a few follow-up studies on this. There was a paper in last year's NeurIPS half a year ago that actually won the Best Paper Award that can be viewed as a follow-up that also talked about how uniform convergence is not a good explanation or cannot explain generalization in deep learning. But pretty much I would say we don't understand the full picture. So so this is still really an open field. And I think it's still, lots of really exciting research problems and mysteries to be understood by the theoreticians. Okay, so maybe I'll take a very quick break here. So this was my small historical tour. Are there any questions? Do I see the chat? Is compression related to, I'm not sure what you mean by sufficiency. So compression size, it's a tool that can be used to derive generalization bounds in the same way as, for example, VC dimensions. So we'll now, for today, we'll talk about VC dimension. I'll give you at least an intuition on how one develops these generalization bounds. And it'll become clear why compression sizes would lead to generalization in the same way. There's two slightly different but related lines of research on compression. So one is compression schemes for a fixed hypothesis class. So here I'm really asking for any function in a hypothesis class, can I compress the label that it shows on a data sample to to a small subset of this data sample. The other aspect is I can ask, independently of a hypothesis class, I can have more of an algorithmic point of view. I can say, does the behavior of my learning algorithm only depend on few points in a data set? So this is, for example, for support vector machines, this can be shown. So this is also a notion of compression that would then lead to a generalization guarantee for the output of this algorithm. So there's, when people say compression sizes, we can talk about compression of functions in a hypothesis class, or we can talk about compression as a property of an algorithm that depends only on few data points in a training data sample. Okay, I hope that somewhat answered the question, but we'll definitely have time also on Thursday to talk more about potential questions. So now what I wanted to do is, now that I told you this this story on how theory developed, or how theory developed in parallel with the development of practical machine learning algorithms, at some point really driving the development of these practical methods, but in the last decade more, I would almost say struggling to explain the now really vast success of the deep learning methods. So what I now will do is I'll take you back to the 70s. So I think it is important to understand the some of the basic principles that are behind these phenomena of generalization. So what I'll do today is I'll introduce you very briefly to VC theory, Wapnick-Cherepanenko's theory, and I'll give you, I hope, at least enough intuition to really understand how this really understand this tool at work. So I guess I have 25 minutes, so try to be brief. Okay, so so let's recall our setup from yesterday. So we are always looking at an instance space, domain space that is, a Euclidean space, a label set. We're still just talking about binary classification, and we're looking here at a fixed hypothesis class that is a subset. I don't know if you're familiar with this notation, but if I say 0, 1 to the x, I mean, this is the set of all functions, all binary functions from x to 0, 1. Right, so a hypothesis class is just some fixed subset of functions from the domain to 0, 1. So what I first need to define is I define what does it mean that my class shatters a set of points u that is a subset of the domain. So what does it mean that H shatters this set of points? It means that if I restrict my class to the set of points, so this is the restriction of my class H to the set U, I get all possible functions over U. So here I have a small illustration. So here, say I have 3 points. So I'm in R2, right? I'm in 2-dimensional Euclidean space. Here I look at 3 points, and I look at the class of linear separators, right? So what I want to show you is that the class of linear separators can shatter this this set of points. So what do I need to show? I need to show that all possible binary behaviors, all possible binary functions can be realized by a linear separator. So for example, my 2 classes here now are red and blue. So 1 is 0, 1 is 1. So if they all should have the same label, right, all points are red, I can just have a linear separator that passes somewhere far away from these points. They all get the same label. If I want to separate this point out, you can see I can separate this point off the other 2 with a linear separator. Same for each of the other points, right? And the same if I want to separate 2 points off, again, I can make 2 points blue and 1 point red. And of course, I can also have them all blue, right? So if we here flip through this again, you get the idea. So shattering means that with my fixed class, here my class of linear, in 2 dimensions, just a line, linear separators, I can get all possible labels over these 3 points, right? So the class of linear separators shatters this set of 3 points. So now the VC dimension uses this notion of shattering. The VC dimension is the maximal size of a subset U that is shattered by the class. Or if H can shatter sets of arbitrarily large sizes, then the VC dimension, we would call the VC dimension infinite. Right, so here again is my example. Linear separators in 2 dimensions shatter this set. So now my first small quiz is, what does this illustration here, so what is this picture that I just showed you, what does it tell us about the VC dimension of half space classifiers in R2? So I think now there should be the Slido quiz 1. So the answers, so my question is, this illustration here that I can shatter these points, what does it tell me about the VC dimension? And I think the answers were A, the VC dimension is at least 3, the VC dimension is at most 3, or does it show me already that the VC dimension is exactly 3? So, so I don't know what are the, somebody needs to tell me the result of the poll. Anybody's collecting the results? Here's something on the chat. Okay, so here on the chat, I see at least 3, exact 3, at least 3, exactly 3. Both of them. Okay, so I'll resolve. I don't have the statistic now on the quiz, but I'll resolve this.
Hi, Ruth.
I
can give you some statistics if you need to. There was 11 voted participants. 9% voted for variant A. 55% voted for variant B, and 36 voted for C.
Okay. Right. So, I mean, so the answer is this illustration just shows us that the VC dimension is at least 3. Right. So here I'm showing you that linear classifiers can shatter a set of size 3. So this means that the VC dimension is at least 3 because the VC dimension is the maximum possible size of a set that is shattered. In fact, actually, in this case, the VC dimension of linear classifiers in 2-dimensional Euclidean space is exactly 3. But for that, we would also need to show that linear classifiers cannot shatter more than 3 points, right? So this illustration just showed that the VC dimension is at least 3. So now I have another small quiz. This is kind of a small useful exercise to get used to this notion. What is the VC dimension of axis-aligned rectangles in R2? So what do I mean by axis-aligned rectangles? So I mean, you can specify in 2-dimensional space, you specify a rectangle, and then we have one label, say this is 1 inside the rectangle, and another label outside the rectangle. So I'm looking at the class of predictors that is defined by all rectangles like this. And I think on the quiz I asked which number between 1 and 6 do you think is the VC dimension of this class? So I'll let you think a little bit, let you play with this shortly. So this class really, this is the class of predictors that are defined by I'm specifying a range in each of the features, right? So in each dimension, I specify a range. I say here, my point should lie between this lower bound, this upper bound, and the other feature, it should be between this lower bound and this upper bound. Then I get label 1, say, if not, I'm outside this specified range in each of the dimensions, I'm outside, it's a negative prediction. So what would be the VC dimension of this class? Any guesses? So my hint was it's between 1 and 6. So again, I need somebody to tell me the statistics. Here's something on the chat. Let's see.
It's me again.
Ah, okay.
So there were 7 participants voted.
Okay.
63% for variant 2 and 38 for variant 4.
Okay. So so the debate is between 2 and 4, and the answer is actually it's 4. And I just want to very quickly take you, I mean, by images through the proof, because it just shows you what do we actually, if we want to figure out what is the VC dimension of a class, what do we need to show? So I'm claiming now the VC dimension of rectangles in 2 dimensions is 4. How do I show this? So the first step is I need to show that there exist 4 points that are shattered. So here are 4 points that I'm claiming are shattered. So I'll convince you by image, right? So if I want to make them all red, then I can put the rectangle somewhere else in the space. Any singular, I mean, you get the idea, right? Any point that I want to separate from the other 3, of course, I can just put a small rectangle around it. Any 2, I can also separate out. Any 3, so I don't go through all possible labelings here, but you get the idea. So we can do all these 3, all 4. We can do all possible labelings on this set of 4 points. So now the next step, and this is important, so what I also need to show if I want to claim the VC dimension is exactly 4, so this again shows me the VC dimension is at least 4. If I want to show the VC dimension is exactly 4, I need to argue that no set of 5 points can be shattered. So here actually, this is a little bit more difficult. I need to have something of a proof. So I mean, I could give you these 5 points and tell you, you know, try to shatter it, and you will not manage. But if I want to prove the VC dimension is exactly 4, I should actually have an argument for why can we not get all possible labelings of, you know, any set of 5 points, right? So and here the argument goes as follows. So if I have any set of 5 points, there's always one that is, you know, leftmost. There's one that is rightmost. There's one point that is the lowest, and one point that is the highest. Right, so in any possible set of 5 points in 2 dimensions, I can identify one where that is, you know, has the smallest first coordinate and so on, smallest second coordinate, largest first coordinate, largest second coordinate. Right, so now once I identified these 4 points, sometimes they can be the same, but the proof will, so one point can be both upmost and rightmost, but it would still be the same proof. So I have these 4 coordinates, and now if I declare these 4 points to be blue, I cannot have this one to be red. As soon as these 4 are blue, this last point also has to be blue. Right, so this is the labeling that I cannot achieve with rectangles in 2 dimensions, and this will be true for any set of 5 points. So this kind of completes the proof why the VC dimension of rectangles in 2 dimensions is exactly 4. So this was just kind of small warm-up exercise so that you get the idea. So now I guess I have 10 minutes and I want to take you at least through a little bit of technical details here that will show us why is this notion, this is a purely combinatorial notion that we can define for any hypothesis class. Why has this become so crucial for our understanding of generalization in machine learning? So so actually I have a few more examples, and I guess I'll just skip through them just very quickly now because we don't have much time left. So here again, I just look at a Euclidean space. So what we already saw in the first example, if I'm looking at linear half spaces in d-dimensional space, VC dimension is d+1. So this is a good thing to be aware of. It's also not very difficult to show. The VC dimension of all predictors. This is the class that I used yesterday for the stubborn learner, right? So the stubborn learner, it could output any function that has some finite amount of ones. So it kept assigning the whole space to 0 except for the points that it had seen in the sample. So if we wanted to look at the class that it outputs, it's a class of functions that map only a finite amount of points to 1. Right, so the pre-image of 1 of any predictor in this class is finite, it's not infinite. But the VC dimension of this class is infinite, right? So one can, once we understand VC theory, we have a new view of why the stubborn learner doesn't succeed. The VC dimension of neural networks, for fixed architecture and say sign activation, is related to the number of edges in the network. So what you want to maybe keep in mind as a rule of thumb is very often the VC dimension of some class of predictors is in the order of the number of parameters that you need to specify a function in this class. This is not always true. There are counter examples, but this is kind of the rule of thumb that you want to have in mind. Right, so in the case of neural networks, it's somehow the number of parameters that is needed to specify the exact behavior of a network with a fixed architecture. Okay, so now the crucial property that actually gives us generalization is what's called the Sauer's lemma. So here, this is don't know how quickly this is readable, but what we're interested in is how many different behaviors can my class induce on any subset of the domain, right? So we know if the VC dimension is D, right? So if a class is VC dimension D, then we know there exist sets of size D or smaller than D where the class can actually induce all functions. right? So up to the VC dimension, we can get 2 to the size of u many behaviors of this class, right? So up to D, VC dimension is D, means there exists a subset U of the domain such that the class can induce 2 to the D many different functions on this subset. But then what this lemma tells us is, from this point on, the number of behaviors that the class can induce actually cannot keep growing exponentially. It grows only polynomially. So this is a very crucial property here. So the number of patterns that H can induce on any domain subset grows polynomially in the size of the subset. And this is somewhat surprising if you think about it. So we define VC dimension is really just combinatorial parameter and talks about what can the class do and small up to VC dimension actually size subsets, right? So we know up to D we can induce 2 to the D behavior, and all that VC dimension by definition tells us is that if we have subsets of size larger than D, then we don't get all. So it's not 2 to the size of this domain set, but it could be anything less in terms of the, just a little bit less in terms of the definition of the VC dimension. But this lemma actually says, no, once we go beyond the size, once we look at larger domain subsets, the number of behaviors of this function class will only grow polynomially. And this is very crucial. So from this property, we actually get that VC classes are Park learnable. So this is a very similar statement to the statement I showed you yesterday for finite classes. So if we look at X as some domain, H is just some subspace of functions of finite VC dimension, P can be any distribution. Then with probability delta is a confidence parameter with probability at least 1 minus delta. That's what we saw yesterday. We have that the here is the supremum over all functions in the class. So this statement will hold for all functions in the class. We have that the empirical loss minus the true loss of this function is bounded by this quantity, which now depends on the VC dimension over n. Right, so we see that this quantity here, that's the generalization error, goes down with the sample size n, and it goes down at a rate that depends on the VC dimension of the class. So I'll now, I want to take it through proof, and I want to build on the proof that we saw yesterday for finite classes. So, so let's maybe recall quickly, briefly, what we saw yesterday for finite classes. So for finite classes, we looked at this here, it's a maximum, now the class was just finite. We looked at what's the probability that for the worst function in my class, the true minus the empirical loss are epsilon over 2 apart. Right, so this is the quantity yesterday that we bounded. So we said, well, this is, we can say this is kind of a big OR over all functions in my class. So I'm here now, if I'm fixing a class, what is the probability that my empirical loss is far away from my true loss? And if you remember, we said, we can bound this by Höfting's inequality, by Höfting's concentration inequality. We use the union bound. So now here came the size of the class into the picture. Höfting's inequality tells us, well, it's different. It goes down exponentially with the sample size, and we got this. So solving here, setting this to delta, solving, we got this bound on the generalization error that involved the size of the class. So this was for finite classes. So of course we want to be able to derive such generalization guarantees, not just for finite classes, but for arbitrary, also for infinite classes. So if you think of half spaces, this is an infinite class, but it has finite VC dimension. So now I should give you a little bit of warning. The math that I'll show you is not entirely correct now, but so it's kind of very hand-wavy math. But it'll give you the essence of why bounded VC dimension leads to very similar generalization property as what we saw here for finite classes, right? So now for VC classes, so this is the sketchy math that I'm doing here. So again, we want to bound the probability that over my function class, the difference between my true and empirical losses is larger than epsilon. So what I'm doing here, so here I cannot, I will not be able to do a union bound here because the size of my class is now potentially infinite, right? So what I'll do instead is I introduce what is called a ghost sample. So I'll approximate this true loss here with another empirical loss that is a sample of the same size, right? So I relate, so instead of here looking at the difference between the true and empirical, I look at the differences between true empirical losses. And now what I can do, instead of doing a union bound over my full class, I'll do a union bound over the behaviors of my function class on these two fixed samples. And so this is where I'm being hand wavy. I mean, one has to argue here that these, that these probabilities actually relate. One has to argue about condition of all possible partitions. So here is, this is kind of a bit of a jump. But the idea is that I can, instead of doing a union bound over my full class, I'll do a union bound over the behaviors of my function class on these fixed subset of my domain. And for this, I have a bounded size. This is what I just showed you, Sauer's lemma. Sauer's lemma tells us, well, this size here, this number of function, it's only polynomial in the size of the sample, right? So here I can use Sauer's lemma to, instead of, I cannot go over my full class, but I do union bounding over the behaviors that I get from Sauer's lemma. And here you see this size of the function class goes in logarithmically into the bound for the finite classes. So if I here take a logarithm, I get d log size of my sample, then I would in principle need to do some more work, but you see that d, my VC dimension, is actually is leading component here, right? So since this is polynomial rather than exponentially in the size of my of this sample, this bound that I got from Sauer's lemma, I'll get here the VC dimension rather than the size of the function class in my generalization bound. So this was very quick hand wavy proof of VC theory. Okay, so now I'll just take 2 more minutes. I want to give you an idea also of lower bounds. So maybe another very basic and very kind of important concept to keep in mind is that every learning algorithm actually will fail on some task. So we have this theorem that's known as the no-free lunch theorem. So if we have any fixed domain, for every learning algorithm, if you look at a certain sample size, there exists a distribution, that meaning there exists a task, a learning task, such that this algorithm on expectation will have a large error. We can make this constant here. We can make it arbitrarily close to half for binary classification. I put quarter, but it really just means, we can, any learning algorithm, for any learning algorithm, there exists a task on which this learning algorithm will fail. And maybe what's important here to point out, sometimes people confuse this with a large base error. So of course we can also not do any prediction if there's a lot of noise in our data generation. So if our labels are very noisy, then no predictor can do well on this distribution. But this distribution here in the no-free lunch theorem is actually pretty benign. It's not a noisy distribution at all. So the labels are deterministic. There exists a predictor that does this particular task perfectly well. So it's not inherently a difficult, noisy task. It's just a task that is bad for this particular algorithm. So this is important to keep in mind. It's not just an issue of noise, but it's an issue of any learning algorithm having what's called an inductive bias. Every learning algorithm is going to be successful on some tasks, but not on all of them. And here the support of this task that we show exists. It's finite. It's just 2n. So it's a pretty benign distribution. It's just that for this particular learning algorithm, this distribution is going to be bad. So I'll take half a minute to just give you the idea of the proof, and then I'll finish. I'm almost done. So we want to show that for any learning algorithm, for any sample size, there exists a distribution on which this learning algorithm will fail. So what we do is we actually do a probabilistic argument. We consider all possible distributions over two endpoints, right? So we look at a finite domain and we look at all possible labelings over these two endpoints. This is what we consider as our possible distributions, and we'll show that one of these, at least one of these, our algorithm will do badly on. So the idea is to make a probabilistic argument. We'll say, well, A gets to see the labels only in half of these points, right? Because my sample size is n, I'm now considering 2n many points. So now what one can argue is that for each of these other points that the algorithm hasn't seen, it has an expected error of half. I mean, on each of these other points, all the algorithm can do is random guess. So there's an expected loss of half on each of the points the algorithm hasn't seen. So now if you, I mean, you'll have to do a little bit more of, more careful math than this, but the idea is, on half of the points, I have chance half of getting it wrong. Well, that gives me an expected loss of quarter. So that's the idea. I mean, of course, one has to do a little bit more of a formal argument here to make this argument proper. But the idea is, well, if I don't get to see all the main points, then I have chance half of getting half of the points wrong. So the consequences of this, so I'll just briefly mention two consequences. One is, I mean, this same proof technique can be shown, can be used to prove lower bounds for VC classes. So we can show sample complexity lower bounds in terms of the VC dimension of any class with a very similar technique. And the other, and I think this is the more important conceptual lesson to take away here, is that there's no universally successful learning algorithm. Any learning algorithm has inherently an inductive bias. So inherently, it's going to be good on some tasks, but it's going to fail on other tasks. And this inductive bias is something that is necessary to be successful on some tasks. If there's no inductive bias, and in the case of the stubborn learner, it'll it'll fail it'll hopelessly overfit. So this is what I want to end with today. So here really the main message is there's no universally successful learning algorithm. Any learning algorithm will be successful on a particular set of tasks, but will not magically solve all our problems at once. So this was my lecture for today. Yeah, and tomorrow I want to talk a bit more about more recent challenges, maybe tell you a bit about my research. I haven't fully decided. I'll talk either about transfer learning, theory of transfer learning, or theory of adversarial examples. Okay, so welcome everybody to my third lecture in the machine learning theory course in the summer school. So, so just to recap the overview, so we had on Monday, we talked about a small I gave a small introduction to learning theory. Yesterday, I told you a bit about history of learning theory, how theory has influenced practice and vice versa. And we saw basic concepts, basic techniques to derive generalization bounds in binary classification. So we saw VC dimension and the bounds we get through VC dimension and no free lunch theorem. And today, what I would like to do is shift gears a little bit and talk about a little bit of current research directions. I'll tell you some of my research as well. And in particular, the main theme here will be learning under distribution shift. So I saw that there's actually several lectures in the summer school who also talk about transfer learning, learning under distribution shift in various applications. So I thought maybe it's interesting to also see this topic from a theoretician's perspective. So in the standard learning framework, so what we've seen so far is, the situation is as follows. We see some data, we fit a classifier, and the goal is to predict well on the new unseen data. And the main underlying assumption here that is present in most of the developments, most of design of machine learning, is that the training and the test data are generated by the same data generating process. So in the theoretical framework, I told you, well, we will, to model this, we view the data generation as a probability distribution over some feature space, or feature space times label space. And we're assuming that both test and training data come from the same distribution. But this is very often, this is not actually the case. And there's a lot of efforts actually to gain better understanding and to deal better with situations where the data generation changes between training time and test time or application time. So here's so this talk will be a little bit of an overview, various directions, various topics where such data shift phenomena occur. And then we'll also talk about techniques to address these. So here are some situations. So one example for that I've actually seen practitioners, people from insurances mention is that before the global pandemic that we're currently in hit, maybe an insurance employed some machine learning algorithm in order to decide which drivers to give insurance, or a bank maybe wants to decide whom to give a loan, and they decide that on certain features of the customers, but the behavior of people, as we probably all experienced, drastically changed in the past half year. So one example is, maybe before the pandemic hit, somebody had to have a stable income in order to gain a loan, but maybe during the pandemic, governments are helping out, and even people that just lost their job may be eligible for a loan. Or another example was, if you're a car insurance, the driving behavior of a customer is drastically changed. And what was before good indication of somebody that somebody should be given an insurance at a certain rate, maybe that's not the same during these times anymore. So that's one situation. Another common situation is if you want to train maybe on a medical setup, you want to train some predictor for a certain disease. Maybe training data comes from one country, and now we want to apply this predictor for population in a different country. Maybe certain characteristics of people, certain measurements, medical measurements changed in different situation, but the same test results may still indicate whether somebody, say, has diabetes or not. Another very common situation arises from the fact that we want predictions that concern people. We want them to be correct on all on various possible subpopulations, and this has given rise to a lot of fairness concerns recently, since these methods, if they are trained on a certain majority group, they may actually not perform so well on a minority part of the population. So we may want to have some sort of interventions that make sure that the predictors that we train, that we use to make decisions that will affect people's lives ultimately, that they perform equally well or have equally good predictive performance, say on some minority part of the population as they do on the majority part. Another situation or another common phenomenon is that the inputs to a predictor, they could actually be manipulated on purpose. So small corruptions on inputs to a predictor may actually cause a predictor to have drastically decreased performance on such inputs. Or we could actually, maybe we've trained a predictor for some tasks, and now we want to use part of our learning framework, maybe even the same data set, to train a predictor for a similar task that is not exactly the same, but is related. We have some knowledge on how these two tasks are related. So for example, we could, you know, maybe we trained an image classifier for cats, and now we want to train an image classifier for dogs. So these are not exactly the same tasks, but they are more similar than, say, training an image classifier for cats and deciding whether a patient has diabetes based on some medical tests. So just to give you a little bit of a view on how we would model these situations. So in the first situation, what changes really is the relationship between input features and output features. So the labeling function has changed, we would say here. So beforehand, certain behaviors were an indicator of people were an indicator that somebody maybe should not be given a loan. Now these same indicators don't have the same implications anymore. So it's really the labeling, the relationship between the inputs and the outputs that have changed here. In the second situation, I would model as a situation where the labeling maybe didn't change, but the distribution over the feature vectors changes. So the distribution over the covariates has undergone some shift, but the relationship between a certain input and the target output has remained the same. So the third situation here is what we know as adversarial learning, or learning under adversarial manipulations. So this is not a naturally occurring phenomenon, but we have a situation where some entity is actually manipulating the inputs with the goal of inducing a mistake on the classifier. And the last situation here that I described is really scenario where the learning task has changed. So these are kind of, all of these are situations where we have a difference between maybe learning at training time and what we want at test time, but they're very different conceptually. We would model them very differently, and therefore they would also require, of course, very different approaches for solution. So, so to give you a little bit of overview on terminology in transfer learning, and I should say that this is not necessarily commonly agreed upon. So there is, so I'll give you maybe an overview on the terminology that I would tend to use, and I don't think it's too esoteric, but it's not written in stone. So some people may use slightly different terminology. So just as a small warning here. So before the terminology, so what is common in all these scenarios, is that the data generation differed between training and test time, and the common goal in addressing these scenarios is that we want to adapt an existing method. So we already had a method that is successful for learning or training a classifier for some task or on some kind of population. And rather than now retraining, maybe preparing a data set, labeling a data set, retraining entirely from scratch, we want to adapt the existing method to now perform well on the new task. So this is what we call transfer learning. So it's this difference between well, realizing there was a change and say, well, now we have to start entirely from scratch. Instead, what we want to do is we want to say, well, we already did well here. Can we somehow adapt and somehow get away with doing less work than training on a new task entirely from scratch? So this is what connects all these different scenarios. And so in terms of terminology, domain adaptation, I would say is usually used for a scenario where we have just two, say maybe a one-step adaptation. So we have some source. So we train a predictor on some task, and the goal is now to adapt it to a different task. We realize, oh, some shift has happened. how can we adapt what we already have to a new scenario. And often in this setting, we are in a situation where we maybe have lots of annotated data, labeled data from a certain task, but we only have unlabeled data from the new task. So if you think of this, say the medical situation, maybe we have a good classifier for a certain disease trained on the population of some country, and now we have a lot of data for the population in a different country, but maybe nobody has sat down yet and labeled all this data. So this is a very typical scenario for what we call domain adaptation. So it's an adaptation from one task to a different task after a shift. So single-shot learning or one-shot learning is kind of a special case of this. So this is something that has always becoming popular in very recent years. So it's essentially a domain adaptation setting where we want to get away with very, very few data points from the new task. So maybe just one labeled example, or maybe just a handful of labeled examples. But here really the emphasis is that we are attempting to doing domain adaptation with very few data points from the new task. Multitask learning is the scenario that I listed last. So maybe on the same type of data set, we actually want to train different classifiers for different aspects of these data sets. So maybe in an image data set, I want to have predictors for cats and dogs and zebras. Or maybe on the same medical data sets, I want to have a predictor for different diseases or different aspects of these patients. Lifelong learning is usually used in a scenario where we have a long sequence of steps. So it's not just a one-time adaptation, but really the emphasis is on how can we exploit a situation where we have a long sequence of small changes, right? And we want to keep adapting to these long sequence of changes. And maybe there's even some pattern in these type of changes, right? So maybe due to the fact that we're seeing many changes, we can actually make use of the type of change that is happening and learn the type of change and therefore perform better and better as we keep adapting. So here really in lifelong learning, the emphasis is on the fact that we have many, that we're doing this, for a long time, and we're gaining experience through many adaptation steps. And then the last scenario, adversarial learning that I put here, this is often not classified under kind of the transfer learning umbrella. But I would still say it's also a situation where the type of data that we want the classifier to perform well on at application time, it's not the same that we had available on at training time. So we need to have some sort of intervention to make sure that the classifier will actually be robust to this type of data shift that may happen at application time. So I want to start, so maybe for the remainder of this talk, so I'll say a few words. I'll start with adversarial learning. I'll say a few words about adversarial learning, and then I will mostly be focusing on domain adaptation. And what I want to do is go through a bunch of common approaches, techniques that people use for domain adaptation, and look at these through theoreticians, through the theoretician's eyes, and analyze a little bit, what are the underlying assumptions in each of these approaches, and what are therefore their maybe advantages and disadvantages. Any questions so far? So this was kind of the introduction. I don't know if there's any. Somehow the chat always disappears. Okay, so there seems to be nothing in the chat, so I'll continue. So as I said, I start with adversarial learning. Okay, so So we've all seen this. I guess, I mean, it started already a long time ago now, 2013. There was this paper that had kind of made a shocking observation. So this was just after, you know, deep learning really took over in, you know, an image prediction tasks. Everybody was very optimistic, and then came this this observation that these predictors that did so well in all these image classification tasks actually could be fooled very, very easily, and could be fooled with inputs that, from a human's point of view, are really look entirely like easy tasks, right? So there were these. So what they did is they took some images, trained a classifier, were performing image classifier, and then turned out if you just flip a few pixels or add some noise to a human, it still looks like the same image, but the network gets completely confused. So what we want in adversarial learning is that the network predictor is not only doing well on the task that it was trained on, but also to some sort of perturbation of these inputs. And the idea is that these perturbations are somehow imperceivable. So the question is, what do we actually mean by this, right? So in images seems clear to us, well, here I don't see a difference between these two images. The network somehow does. So what does this mean? What does it mean that it's a small perturbation? So there are two, so now, of course, people have started working on this, and I would say there may be two main approaches in practice. So we can either pre-process the training data or post-process an already trained predictor, right? So what is, I think, very popular and successful in practice is that we take the training data and we already add these perturbations to our training data set. Oh, there's a mistake in my. So the data is augmented with the perturbed instances. In post-processing, the alternative approach is to say, well, we already have a predictor. We want to make sure that it doesn't suddenly changes prediction on small changes. So we somehow want to smooth out the behavior of our trained predictors. So this is what I think are the main approaches in practice. So in learning theorists have, you know, started to look at this very recently and kind of develop various cases, various upper and lower bounds for adversarial learning with loss functions that are induced by the type of distributions. So the type of perturbation. So depending on how the type of classifier and the type of perturbation interact, this learning scenario can become much more difficult than learning with respect to a standard binary loss, or it can actually be roughly the same, right? So let's so I want to just give you kind of a small view on how we would model this from a theoretical point of view. So here is now I'm taking you back to the learning theory framework. So this is what we've seen, right? So we say, okay, our instances are maybe some feature vectors in a d-dimensional Euclidean space. We have a binary classification task. We already we saw that we need to typically restrict ourselves to some fixed hypothesis class. So here it could be, you know, neural networks of a certain architecture. And so now we train some predictor on this data set. So say this predictor does perfectly well here in this situation, does perfectly well on my data. So in binary classification, the typical binary classification loss, we say, well, the predictor makes a mistake if it misclassifies one of the points, right? So if this point here, this now red point, is actually on the wrong side of the decision boundary, the binary classification laws would say, well, this we will hold against the predictor, right? So the adversarial laws is actually much more strict. So what the adversarial laws does, so we can phrase this as follows. We're saying a predictor. So again, so I'm phrasing a loss function now, and if you remember, a loss function is always a function that takes in a predictor and an input and an output, right? And so we're saying that the predictor suffers adversarial loss if there exists a point in the set of admissible perturbations. So here U of X, I'm calling all the possible perturbations that we would consider as imperceivable on this instance. So if there exists an instance X prime, so X prime would be sitting here on the other side of the decision boundary, such that the predictor on this instant X prime has a different label than the label that was observed in the instance, right? So, so what you can see here is that the adversarial loss, so is actually, we are paying adversarial loss in these two situations. So we're also paying adversarial loss if we make a mistake, as before. So if a point was a mistake, if we made a mistake on a point, then this X prime is just the same X, right? So, so if we're making a mistake on a point itself, then this condition will hold. If the perturbation, if X is always an admissible perturbation to itself. And the other situation in which we pay adversarial loss is if a point sits close to the decision boundary of the predictor, and close is now not necessarily measured in terms of our usual metrics. So here in my picture, I mean, it looks like it's just a ball, but this could be something different. So this really depends on what we consider an imperceivable perturbation in the specific task that we're looking at, right? So this could be modeled in various ways. So for example, through small perturbations in terms of a norm, but it could also be something very different. So we're paying adversarial loss if either we're making a mistake on a point, or a point sits close to the decision boundary, where closeness is now measured in terms of the perturbation type of our adversary. And the consequence of this, so this is actually, I think this is good to become aware of. So if we're requiring this, if we are now strengthening our requirement for a classification task, so that we want small adversarial loss, so we should realize that no matter what the predictor does, it will suffer loss in all of this margin area, right? So no matter what the predictor does, as long as there's no chance for the predictor to go through really a zero, an area of zero support with respect to the distribution, even if the predictor can, from the binary classification point of view, perfectly well predict the task, the adversarial loss may actually be positive. So this is I think it's good to become aware of this phenomenon. That adversarial training with adversarial robustness is really much stronger requirement than just training to get a small classification loss. Right, and as I mentioned, there have been various studies now looking at these learning with respect to this new loss function. So I just want to highlight one of my recent works. So we, in a recent paper this summer, actually, ISML, we did actually VC analysis, and we showed that if the VC dimension of the class and the VC dimension of what we call the margin class, so we introduced a set of subsets of the product space, actually, that is would be the margin class that is induced by the perturbation task and the classifier task. If both of these has finite VC dimension, then we can then we get a pack learning type result. So then we have distribution-free proper learnability with respect to the robust loss. There had been actually in COLT last year. COLT is the main machine learning theory conference. there had been a paper, Montasa, I think Haneke and Srebro, that showed that in general, it's not possible to properly learn with respect to an adversarial loss. They also had a positive result that if we don't have this requirement of proper learning means that we have to output a classifier from the task, which is, if you think about what we talked about yesterday, we were analyzing empirical risk minimization paradigms. So typically we would output a classifier from the task that we're currently having in mind for a specific task. So most of our typical learning frameworks, that they would be considered proper learning. So it was an impossibility result. So we showed that if the margin class also has finite VC dimension, then we get the typical upper bounds for learning under an adversarial loss. And what we also did, I think there's still lots of really interesting research directions in this area. So what we also then did in this work is we introduced kind of a notion of a query efficiency of an adversary. So you can think of, I mean, typically you're in a situation where the network that was trained, maybe to the user or to the adversary, it just, you know, it acts as a black box. So it can send queries to this predictor. It gets out a label, but maybe the adversary that is interacting with this predictor doesn't actually, you know, have access to the network itself, to all the weights and so on. So maybe it has only query access to this network. It can, you know, send in examples and get out predictions. So one can actually think of adversarial robustness also as follows. Maybe we're not so concerned with this type of property here. So with this type of loss, so this type of loss really, it just talks about existence of point that is close but across the decision boundary. But instead of being so strict, so this is really a requirement that will in many situations result in a high loss. We could say, well, maybe we don't care about this existence here, but what we want is that we train predictors where the adversary that has to find adversarial examples has a high query complexity. So we can, so we started analyzing query complexity of adversary types for various predictors and various perturbation types, and also showed that this is right now, it's, you know, it's a very restricted result, but it's kind of a first step, that if we have a query efficient adversary, then we can use the existence of this adversary to actually design a compression scheme and get a learnability result that employs the query efficient adversary. So I think this is still an area where there's lots of interesting research questions for anyone interested in getting more fundamental theoretical understanding of machine learning. So so now for the rest of the talk, I want to focus on domain adaptation. So I've worked quite a bit on developing upper and lower bounds for various transfer learning domain adaptation setups. So what I want to do now is I'd like to take you through you know, 4 kind of main paradigms that are maybe used for or used in practice for domain adaptation, and look at them from a theoretician's point of view, and analyze what are their underlying assumptions, and therefore what are maybe their advantages and disadvantages. So so just to recall, so domain adaptation, we're looking at a scenario where we trained a classifier on some task, and now we observe, or maybe we tested, that there was a shift in the data generation, and now we want to adapt our classifier to perform well on the currently generated type of examples. Any questions up to here? Okay. Okay, so let's have a look at how would we formalize domain adaptation. So here's our formalization of binary classification now turned into the domain adaptation framework. So again, we have a domain or feature set, which we still call X, and we are still in a binary classification task. But now we're dealing with two distributions. We have the source distribution, which is the task that we either have lots of label data from, or maybe we already trained a classifier on, and then we have the target distribution. And typically we would assume that while we have label data available from the source task, and maybe we have a predictor already trained on the target task from the source task, from the target task, we only get to see unlabeled data. Right. So this is kind of the framework in which domain adaptation is typically modeled. So we have labeled data from the source task, maybe a predictor from the source task, and some sort of unlabeled data from the target task. And the goal now, so we want to come up with a predictor that has a small true or small expected loss. But now the focus is on the target task. So given these inputs, labeled data from the source task, unlabeled data from the target task, maybe a predictor trained on the source task, we want to come up with a predictor that has small loss with respect to the target distribution. And we're measuring ourselves with respect to the best possible loss that is achievable with our class in the target distribution. So that's the setup. So first, kind of a very obvious observation. So if we're not making any assumptions on how the source and the target relate to each other, so if we're just considering a general shift scenario, then there's not much we can hope for or that we can guarantee, right? So if you look at this this situation here, we have labeled data maybe from our source task. Now we have something, some unlabeled data collected our target task, but we don't have an idea on the labels. Maybe we trained this on the source. Now, if the label shifted and the covariance shifted as well, and the target, our source predictor could be arbitrarily bad for the target, right? And so, in the a good target predictor could be very, very different from what is good on the source. So this is pretty obvious, but it's good to keep in mind. So we have to make some sort of assumptions on how the source and the target are related. So a typical assumption, or typical first assumption actually that that is often made in theoretical studies on domain adaptation, and it's also actually justifiable often in practice, is the covariate shift assumption. So covariate shift, essentially it means that the labeling between source and target doesn't change. So maybe there's a shift on the feature vectors, on how the feature vectors are distributed, but the relationship between how the feature vectors relate to the output, to the labels, remains the same. So this seems like a strong assumption, and it seems at first sight it may seem that this will turn the domain adaptation problem immediately to an easy task. If the labeling is the same, I learned the labeling on the source, and of course it could seem that, you know, then I should be doing fine in the target as well. So here's just again in pictures a small illustration why this is not solving the problem yet. So if we're in this situation, right? So here's my my labeled source data, and here's my unlabeled target data, and I'm promising you that there is a predictor that does perfectly well both on source and target. So there is a predictor that reflects well the labeling, the relationship between feature vectors and outputs at the same time, does well at the same time on source and target tasks. Of course, in this situation, that promise doesn't hold that much, right? So if I now just learn something on the source, this looks like a reasonable predictor, kind of a large margin linear separator on the source task. This could be, of course, arbitrarily bad on the target task, right? If I haven't seen any labels on the target, even though there was a predictor that does really well on both source and target at the same time, as long as I'm in this situation, I cannot tell, right? So just the covariate, that's important also to keep in mind. Covariate shift at first sight sounds like a strong assumption, and sounds like this should already get us somewhere, but in itself, it doesn't say much. It still remains essentially an impossible problem. Okay, so no matter what we do, we'll have to make even additional assumptions if we want to develop any successful methods or get any sound theoretical guarantees on these approaches. So first lesson learned here is that to address data shift phenomena, we need knowledge on the type of the data shift that has happened and on the relatedness between source and target task. And typically in practice, really what you want to do is probably you want to have some sort of combination or going back and forth between testing and adaptation phase. So it's also maybe good to keep in mind. Okay, so now I want to, okay, I have 12 minutes. So maybe we'll not get to all 4 methods, but well, at least, you know, maybe the first 2 we can, I can discuss with you. So here are 4 typical approaches that I want to discuss. So first is re-rating. So one very, very popular approach is let's re-rate the source data to somehow reflect the target data. The second is model distillation. So here we are using an already trained predictor on the source to now label the target data and see how far we get with that. The third approach is to use a mapping of both source and target task into a joint feature space. And then the last approach I want to mention is this number 3, really it requires knowledge of what could be a good mapping into a feature representation where both source and target look the same. What is currently, especially in the deep learning community, often used or attempted is to actually learn this feature map representation, right? So so these are 4 common approaches that one could invoke to address the domain adaptation problem. So let's start with looking at re-rating approaches. So the idea here is that we have this label data from the source task, and the idea is to somehow re-rate, to use density ratios to estimate the density ratios between source and target, and then minimize a re-rated risk to get a good predictor over the target task. So here we use the data points that we collected on the source, and we're re-rating them with these density ratios. And what is nice here is that this gives us an unbiased estimate of the target loss. So if we actually had access to these to the correct density ratios, right? So if we know exactly what to re-rate every point with, then this gives us an unbiased estimate of the target risk. So this looks very promising, of course, right? So kind of now all the work left to do is to actually get good, have an idea on what are these density ratios, right? So if we have access to these density ratios, then it's essentially our problem is solved. So now let's look at the underlying assumptions of this approach. So the hope is that we can actually estimate the importance weight based on unlabeled data. So unlabeled data is of course always cheaper than labeled data, right? So annotation is actually usually requires human time, human work, human knowledge. So that's an expensive task, or it's an expensive part of the machine learning pipeline that we would, if possible, like to prevent, right? So importance weight, if we just look here again, these are just functions of the feature vectors. So we don't need labels for these. So the hope is maybe we can estimate these weights based on unlabeled data, and therefore get away without having to label the target data. The issue is that reliable importance weights really require unrealistically large amounts of data points, and I'll try to convince you of that. So let's look at the underlying assumptions of this approach. So here in the upper right corner, reminding you of what the approach is, we want to minimize a re-rated source sample in order to get a predictor that will perform well on the target. So now the requirement, of course, if you just look at this formula, one requirement is that these density ratios, that they don't grow to infinity, right? Or in other words, what we need to prevent is that the source density disappears to 0 where we have positive target weight, right? So here we cannot consider points where the source actually doesn't have any support, where the source density would be 0. And we're also assuming for this, for this to be an unbiased estimate, what I was claiming to you before, we're making the covariate shift assumption. We're assuming that the relationship between features and outputs remains the same in source and target. So we're in this situation. So this bounded density ratio assumption, that kind of prevents the bad example that I was showing you before, where the target was just sitting somewhere else. And then, of course, even with covariate shift, we don't know which predictor to use if we only see labels from the source. So now this bounded density ratio assumption kind of forces the target to only sit in areas that are also covered by the source. So now there's kind of two issues with this approach. So one is the density ratios are difficult to estimate. And the other one is, if we now look at this example, one could say, well, why is re-rating even needed? Because now the target is just sitting where the source is. Can't we just use the source predictor? Why do we need to do this, trying to estimate the density ratios? So I want to have a look at these two questions. So first is really kind of a warning that density ratios are very difficult. Density estimation in itself is a very difficult problem. Density ratio estimation is not going to get any easier. So we have this was a while ago, 2012. We had a result where we showed that if we're in kind of a distribution-free, we want finite sample bounds type of framework, then it's impossible to distinguish between a case where the density ratio is 0 and the density ratio is 1 for all points in the domain. So this is actually, it's a very strong lower bound. So not only are we saying, well, you can't estimate them so and so well, we're saying, well, you can't even distinguish these two drastically different cases where all the density ratios are 0 and all the density ratios are 1. So just to give you like a quick idea of the proof, so just in picture, so we were looking at a situation where, say, the source, so we have some source task, it has some labels, and we're promising you covariate shift. The target task has the same labels as the source. So now you get to see but the idea here is that the target we're promising is either all blue or all red. So now you get to see a labeled data set from the source. You get to see unlabeled data points from the target. So now, as long as you don't have collisions here, as long as we don't get to see the same point in both source and target, we will not be able to tell whether the source is sitting, here in this example, the source is sitting on the blue, but just from this information, labeled data from the source, unlabeled data from the target, you cannot tell whether the source is blue or red. The target is blue or red. And for collisions, so this is kind of a birthday paradox type of calculation, right? So in order to have good chance to see actually a collision, you need to see order of square root of the domain size. And if the domain size is infinite, this is just an impossibility result. And then one can turn this type of impossibility. Of course, now one can say, well, this seems kind of silly. The source doesn't have any structure. one can turn this into a lower bound that will take into account the smoothness of the labeling, right? So, so one can either say, well, it's an entirely impossibility result in a discrete setup, or in a continuous setup where we're assuming a smoothness on the labeling relation. This will be, you know, a kind of a quantified lower bound in terms of the smoothness of the labeling relation. Yeah, so I'm running out of time, so I think I'll finish the density ratio, and then maybe I'll have to do some skipping. So the other question I wanted to ask is, why is in this situation, if we're already making this assumption here, why is density, why is reweighting even needed? Right? One could say, well, can't we just use the source learned classifier? And indeed, one can show that if you have a consistent method, if you have a method under these assumptions, bounded density ratio and covariate shift, that where as we see more and more data, my source risk converges to 0, but this is important, it needs to converge to 0, then the target risk also converges to 0, right? So then we can use the same type of predictor, and the target risk will converge to 0. And of course, the rate here will depend on how on the magnitude of these density ratios. So this is kind of optimistic, but here this is a strong requirement that we can actually have a method that where the source source risk will converge to 0. So here, if it doesn't actually converge to 0, if we have a positive approximation error of our class, then reweighting can actually make sense. So let me also just convince you of this in picture. So if we're in, so this is again our situation, source and target. We learn some predictor on the source. Say we also have these labeled examples from the source. So we wanted to use this type of predictor, say a linear predictor, so the source cannot get all of them correct at the same time. And now the source decides, well, here, this seems to be kind of the heavier part of the population, so I'll sacrifice this part in order to get this larger part correct. But now it really makes a difference on where the target is sitting, right? So now we can imagine a situation where if all the target points, we get to see unlabeled target points on the, unlabeled points from the target. If it turns out they are all sitting here, well, then actually reweighting would make sense. So then this, this combination of data points labeled from the source, unlabeled from the target, really tells us, well, pay attention to these points in the source rather than to these points. Right, so this is kind of formally, if we wanted to phrase this formally, if we have a larger approximation error, if we're not guaranteed that we have a consistent source learning, then it can make sense to actually consider a reweighting. So to summarize this, so reweighting the source is one common popular approach to address domain adaptation. So the input here is labeled data from the source, unlabeled data from the target. The assumptions are covariate shift and bounded density ratios. Issues are density ratios require a huge amount of data in general. And under these same assumptions, consistent learning on the source, if it's consistent, if we have risk that converges to 0, may actually already solve the task. If we are not, if we have a positive approximation error, then reweighting may make sense. So now I guess I'm out of time, but I'll just very quickly take you through this model distillation. This is actually an approach that I would claim it works under the same assumption. It's much easier. So the idea here is we have the same assumptions. So consistent learning on the source of phases, but maybe require complex predictors. So if you want a simpler predictor, then you can do the following. You take your label data from the source, unlabeled data from the target. You learn a predictor on the source, something that is complex, maybe nearest neighbor or large neural network, and then you use this to label the target data. So this is has actually a very similar effect as the reweighting, but it's in practice, I would claim this is much simpler. You just train something on the source, use it to learn your target data, train now with the new target data. So if the complex predictor is consistent on the source, we get formal guarantees on the target, just as we in this case did for reweighting. The simpler, but the focus on the simpler predictor could be required for interpretability or speed at prediction time reasons. So sometimes it's desirable to have a simpler predictor on the target than complex neural network or complex nearest neighbor classifier. And in this situation, another comment I would like to make is that the rate ratio requirement, we can actually overcome it with active querying. So have some work on how to use this model distillation approach, and also how to actually incorporate active querying to overcome the density ratio assumption. So here, my summary here is that this is in principle, this is very similar paradigm to the reweighting, but I would claim it's simpler and it works roughly under the same assumptions. So now I think I'll have to skip, so I'll just go to my summary slide. So I'll skip lots of this. Okay, concluding remarks. So what I really want you to take away from this is that knowledge, so in the domain adaptation setup, knowledge about the relationship between source and target is necessary. So this could be relationship between how the labeling changed or how they related, between the marginal distribution, what type of covariate shift has happened, some sort of invariance, or maybe you have a knowledge of a feature representation in which the problems look similar. And also an important question to ask is, are the assumptions on the relatedness, is it testable? So ideally, you want to work with types of relatedness that are actually testable and develop tests for those. Of course, you want to ask yourself what type of information is actually available from the source. Maybe can you actually have some target data, target labels that may make the situation much easier. And another important question is, how frequently is adaptation required? Is it a one-time thing, or are you actually in a lifelong learning framework where you may profit from the fact that you see a long sequence of changes and can maybe learn something about the type of the change. So I'll end this with kind of no free lunch type of message. So there are different types of data shifts. So if you're in have a transfer learning task, it definitely it's worthwhile thinking really about, what type of data shift do I actually have? Therefore, what type of method should work? There are a collection of algorithmic approaches to address these setups, and some are actually quite simple. So I would claim the model distillation is a very simple approach to employ. So definitely worthwhile trying. Which one is suitable depends on the task, depends on how they're related, and what type of predictors is used. And each approach can fail badly if they're used in the wrong situation. So whenever you see somebody selling a new transfer learning, new domain adaptation method, I would always ask, what can you explain? What are the underlying assumptions here on the type of shift that has happened? So that so I really want to promote that, if you develop a new transfer task, you should also at least intuitively explain what is the type of shift that has happened, so that it actually people that are in a similar situation can ask themselves, well, do we have this type of shift? Do we have that type of shift? Are there maybe tests available for these for the type of shift that has happened? So that is sorry for the rush in the end, but I'll conclude with this.